In the boundless abyss of deep space, thousands of light-years from Earth, amidst bright stars and dark dust clouds, two mysterious celestial bodies are orbiting each other in defiance of the classical laws of physics. The echoes of their movements reach us through thousands of light-years, although the bodies themselves are incredibly small by the standards of the universe. The space around them is distorted, forcing even unstoppable photons to deviate from their predetermined trajectories. The flight of these objects is so rapid that time slows down for them, and titanic tidal forces crumple the surface, covering it with folds and cracks. It's a rare and amazing sight, even by the standards of the infinite universe. So let's take a closer look.
Cosmo.
First outer space. 3,200 light-years from Earth. The constellation of Puppis. Distant past. The lives of two red giants are coming to their end. Before our eyes, one of them is making a transition to a new stage of stellar evolution. The fuel in its interior is almost depleted, and the star is beginning to cool rapidly. The delicate balance between the forces of gravity and the fury of a thermonuclear explosion is irreversibly disturbed. Trillions of tons of stellar matter start to get unstoppably attracted towards the center of the star. This process unleashes the uncontrolled thermonuclear fusion reaction in the star's interior again. The powerful explosion rips the star apart, leaving a super-dense core in the center, which is red-hot at incredible temperatures. The force of the shock wave irreversibly changes the structure of the stellar matter, destroying its atoms completely. They're compressed into a super-dense matter, generating countless neutrinos. There remains a tiny but extremely massive clot of matter in the place of the destroyed giant. Around it, the outer shells of the former star explode in a tremendous cloud, turning into a scattered gas nebula. These collide with another red giant nearby at a great speed. This causes this other star to flare up like its companion, which has just ceased to be. And when the echoes of the double supernova dissipate in space, only a pair of mysterious objects remain, almost invisible against the vast emptiness of space. This is how a big catastrophe produces extremely rare and unusual cosmic objects, which we call neutron stars. At present, only a few thousand celestial bodies of this class have been discovered, a minuscule number compared to ordinary stars. And to understand why they are so rare, we need to study the evolutionary paths of stars. According to today's concepts, the life of any star is determined almost exclusively by its mass, with the star's mass being less than 8 solar masses. Having completed several evolutionary stages, it eventually turns into a white dwarf. It is assumed that after billions of years, it will lose the rest of its energy and transform into a hypothetical object called a black dwarf. This path is destined for more than 99% of the universe's stars, including our Sun. If the mass of a star exceeds 8 solar masses, however, its evolution follows a different path, eventually resulting in a supernova explosion. The outer shells of the star are scattered in the surrounding space, forming a scattered gas nebula. At the center of the system, there remains a super-compact and extremely dense object, the former stellar core. Its fate also depends entirely on its mass. If it is too great, the core of the dead star will not be able to resist the inexorable gravity and will inevitably shrink into a black hole. However, there is another way. In the case where the mass of the stellar remnant is within the range of 1.4 to 2.2 solar masses, a neutron star is formed. Gravitational forces in its interior destroy atomic nuclei, forming a super-dense neutron matter with rather bizarre physical properties. For a number of reasons, neutron stars are extremely difficult to observe and study. Firstly, celestial bodies of this class are extremely rare. According to calculations, there is only one such object per 1,000 ordinary stars. Secondly, they are very compact and practically do not emit light in the optical range. Therefore, before the advent of X-ray telescopes, it was impossible to spot these objects. Not surprisingly, the first neutron star was discovered only in 1967, several decades after the theoretical justification of their existence. This is largely due to an unusual phenomenon associated with the law of momentum conservation. Thanks to this effect, most neutron stars have a very high rotational speed, and the interaction of their magnetic and electric fields generates powerful bursts of radiation, repeated with a very clear periodicity. Such objects are called pulsars, and they make up the majority of neutron stars discovered so far. Their pulses are effectively detected by X-ray telescopes even at distances of thousands of light-years. In total, more than 3,200 neutron stars have been discovered so far, and about 90% of them are single objects. The rest are part of binary and multiple systems. Most often, the companion of these cosmic bodies is a red giant or a main sequence star, but in isolated cases, another neutron star. This happens when two similar stars synchronously approach the end of their life cycle, and the explosion of one of them triggers the collapse of the second. Because of the loss of energy during the transformation, the remnants of stellar nuclei closely converge, which causes their mutual velocity to grow to enormous values. And according to today's concepts, this is how the amazing system called PSR J0737-3039 was formed. It is located at a distance of about 4,500 light-years from Earth and is quite unique, being made up of even two pulsars located very close to each other. The first of them is 34% more massive than the Sun and has an incredible speed of its proper rotation. Every second, the object completes 44 revolutions around its axis. The second pulsar is a little smaller and slower. Its mass is 1.25 of that of the Sun, and the rotation period is 2.77 seconds. If we want to take a closer look at these objects, we will see that their size is extremely small by space standards. Either component of the system is no more than a couple of dozen kilometers in diameter. As for their mass, it is actually comparable to that of most known stars. Due to these factors, the density of the matter that the pulsars are made up of is extremely high, and in order to understand this question, we need to look into their interior. The use of mathematical modeling techniques, combined with the theory of neutron star structure, allows us to learn even things not immediately visible. The outermost layer of objects of this class is the atmosphere. Incidentally, however, for neutron stars, this concept differs significantly from the familiar sphere of gas a planet is enveloped in, like that of Venus or the Earth. For both components of the system we're looking at now, this layer is no more than a few millimeters thick. This situation is typical for the absolute majority of neutron stars. But the youngest and hottest objects of this class may have an atmosphere of several dozen centimeters. It's made up of plasma, highly ionized remnants of stellar matter. Most of it is hydrogen and helium atoms, but heavier elements are also to be found. The next layer is the outer crust, which can be several hundred meters thick. The gravity in this region is not strong enough to overcome the electrostatic repulsion between electrons and protons, but it is enough to destroy the usual structure of matter. Elementary particles are all jumbled together, but still retain their internal integrity. Several powerful forces are pulling on the outer crust at once, such as gravity, magnetic field, electrostatic repulsion, and centrifugal inertia. This combination places the surface of neutron stars under constant mechanical stress. Occasionally, it builds up to a point where starquakes occur, titanic deformations of the surface of the cosmic object. As a result, there form mountains a few millimeters high and cracks up to a centimeter wide. These numbers do seem insignificant, but at extremely high gravity, a centimeter-high mountain is comparable to Olympus in the conditions of Mars. If we go still lower, we will see that this layer has no clear boundaries and goes several kilometers deep into the neutron star. As we dive into its interior, the pressure gradually increases, causing more and more electrons to be pushed into the atomic nuclei, initiating a reaction with protons. As a result, a neutron is formed, as well as a highly evasive particle called neutrino, which almost immediately leaves the interior of the celestial body, taking excess energy with it. In turn, beneath the inner crust, there lies the outer core, which consists entirely of neutron matter. This amazing substance is a multitude of tightly compressed neutrons, and its density is 10 to 15 times higher than that of the atomic nucleus. For example, our planet, compressed to the same degree, would have a radius of only 150 meters, and a cubic centimeter of its volume would contain several billion tons of neutron matter. In both components of the system we're looking at, the outer core continues as far as the center of the object. Incidentally, particularly large neutron stars should also have an inner core, according to today's concepts. Its structure is still a subject of scientific debate. According to one hypothesis, the pressure in the center of massive stars can be so great that it is capable of destroying even neutrons, forming a hypothetical quark matter. Such an object is called a quark star. Other assumptions allow for the formation of hyperonic or kaon nuclei, consisting of some bizarre matter with highly unusual properties. However, all these amazing structures are still within the domain of hypotheses, and to prove or disprove their existence is not yet possible. If we look at the system as a whole, we will discover several surprising and intriguing facts. First of all, we can notice that according to calculations, the pulsars in this system are moving rapidly around a common mass center along moderately elongated and very compact orbits. Observations show that the average distance between the components is only 800,000 kilometers, which is almost half the diameter of the Sun. Because of this small distance, the speed of mutual motion of both objects is very high. It exceeds 300 kilometers per second, so the pulsars make a complete revolution around a common mass center in just 2.45 hours. Such rapid motion causes a number of unusual phenomena due to the effects accounted for by the theory of relativity. For example, observations show that at the moment of maximum convergence of the pulsars, the period of proper rotation of each of them temporarily increases by 0.38 microseconds, after which it returns to the previous values. Even though this effect cannot be explained from the point of view of classical physics, the theory of relativity predicted it long before its practical detection. This anomaly is associated with the relativistic time dilation, which becomes the strongest exactly at the moment of maximum convergence of objects. Another phenomenon that stands out occurs during mutual eclipses and is associated with an anomalous redshift detected in the spectrum of one of the pulsars. The point is that the gravity of the component closer to us interferes with the signal from the distant object passing by it. Because of this, the radiation loses energy and its wavelength increases. It is also known that the orbits of these celestial bodies are affected by their interaction. This is reflected in the fact that the point of their maximum proximity, called the periastron, is constantly shifting. This phenomenon is called relativistic shift and has long been known to astronomers. It is usually recorded when studying fast celestial bodies. For example, Mercury's orbit shifts by 43 arcseconds every 100 years. As for the periastron of the binary pulsar, it shifts 140,000 times more strongly. Within a year, it deviates from its previous position by as much as 17 degrees. Thus, PSR J0737-3039 has the highest relativistic shift among all stellar systems known so far. If we leave the dry figures for a moment and think about hypothetical planets that may be hiding in this amazing system, their existence seems rather unlikely but still possible. Some objects, far from the center, did have a chance to survive the crushing double explosion of the supernovae, while others may have formed later. It is still harder to answer this question due to the fact that none of the widespread methods of searching for other planets are effective for exploring such systems. In any case, we cannot speak of the viability of the hypothetical celestial bodies of this system. The freezing cold and deadly radiation make them extremely inhospitable places. Observations show that this binary pulsar is constantly generating gravitational waves, causing the distance between its components to steadily decrease by 7 mm every day. This phenomenon occurs in all physical multiple star systems, but is usually too faint to be measured with any degree of certainty. This tells us that in about 85 million years, the pulsars will merge together to form a black hole. The tremendous cataclysm will be the source of super-powerful gravitational waves that will travel through the entire Milky Way and reach other galaxies far beyond it. And the flash accompanying the merger may briefly become one of the brightest stars in the Earth's sky. In any case, the echoes of this devastating explosion will eventually fade without a trace in the infinity of the universe. Dear friends, lately our new videos on the channel haven't been posted as often as we'd prefer. After all, this is the result of hard and time-consuming work of many people. It takes more and more effort and time to make new ones because we're trying to improve and make informative videos of the highest quality. Your support is the main motivation that helps the channel to move forward. So if you like the result, do tell us about it in the comments. Please feel free to give us your sincere likes, and new informative episodes will not be quite as long in coming. And let's keep in touch.